Welcome
All
to
right.
the Adirondack Sky Center,
And
inspiring than the night skies in the Adirondacks. It just makes sense to start your visit to the wilderness above with us. Our current programs focus on immersive experiences for audiences of all ages. They reach as close as into our own community and as far away as students from around the globe. From inspiring presentations given by some of our friends as world experts, to our Keystone 4-day astrophotography conference, there's something for everyone, including live as well as virtual stargazing, customized programs for schools, and private events. In the case of the Adirondack Sky Center and Observatory, the sky is certainly not the limit, but only the beginning. A second building is currently in the planning stages in the form of an Astro Science Center and Planetarium. This 18,000 square foot building will be dedicated to the study of astronomy and space travel. The planned $15 million Astro Science Center will feature a state-of-the-art planetarium under a 30-foot dome, a 100-seat theater, and a large area for hands-on and interactive activities. Our many exhibits will include a Foucault pendulum, overhead models of the solar system, and historical permanent as well as traveling collections. It's our mission to make this an immersive experience for everyone. You will never be told to look and don't touch. This new building will be in addition to our existing roll-off roof observatory, which houses 4 permanently mounted telescopes. The final phase of construction includes a traditional observatory dome housing a new 22-inch research-grade telescope. Please contact us to become a member or make a donation to help build this new Astro Science Center and Planetarium and begin your journey to the wilderness above. And with that, I'd like to welcome everybody tonight to the September installment of the Cygnus series presented by the Adirondack Sky Center and Observatory. My name is Seth McGowan, and I'll be your host and moderator tonight, and I'm sure you'll be enthralled by tonight's program if you're not already just saturated with anticipation after we made you wait for a couple of minutes. So I appreciate your patience while we solved some technical difficulties. It doesn't happen often, but when it does, it always happens at just the right time. So that's how we decided to do it tonight. Throughout the evening, I'll be putting some links in the chat. You may already see our website, our phone number, and some other stuff. But I'll be populating the chat area throughout the evening with some interesting with some links for you to our project, our Facebook page, and so forth. So have a look at those. And certainly feel free to communicate with me or each other during the night during the presentation, and we'll have a good time. Before we begin, you'll notice your microphones are muted, or at least I recently did mute everybody after coming in. We'll have a Q&A after the presentation, and as always, tonight's presentation is being recorded and will be posted on our YouTube channel within a few days. Tonight, Measuring the Universe with Exploding Stars is presented by Eileen O'Donoghue, who's a Henry Priest Professor of Physics at St. Lawrence University. She received an Associates of Arts degree at Colorado Mountain College, BS from Fort Lewis College, and her MS and PhD in physics at the New Mexico Institute of Mining and Technology. Her research is primarily in radio astronomy, and she's conducted observations with the Very Large Array and Arecibo radio telescopes. In her spare time, and I say that jokingly, especially tonight, she writes an astronomy column for the Adirondack Daily Enterprise entitled "The Wilderness Above." She is a member of the International Astronomical Union, the American Astronomical Society, the Royal Astronomical Society of Canada, the Astronomical Society of the Pacific, Sigma Pi Sigma, Astronomical Society of New York, and most importantly for us, she is a board member of the Adirondack Sky Center and Observatory. So with that, measuring the universe with exploding stars, please join me and welcome Dr. Eileen O'Donoghue. Take it away.
All right. So let me bring up my PowerPoint here. So hello, everyone. Again, my apologies for the glitch. I had a computer emergency and sped all the way back to my office at the university to give this presentation. So I hope you all enjoy it. I'm going to talk about the lives of stars and why they explode and what kind of explosions we're interested in, what information they give us, and then why do we want the information that they give us. So stars begin as clouds, massive clouds of gas and dust. If you look at the constellation of Orion, which is up in the early mornings now, the whole constellation is actually immersed in a huge cloud of gas and dust. And within it, there are star formation areas, regions where stars are forming. In particular, the Great Nebula of Orion, the one in his sword, that is where there's lots of star formation going on. And there's these bright blue stars and they're heating up the gas and dust. And it's a very active region. And so this has been happening for the entire, about 13.3 billion years of the life of the universe. So it's gone on for a long time. Our sun is a product of one of these clouds collapsing. And so with our computers now, we can simulate what the collapse looks like. And so this dimension, 82,500 astronomical units, this is 82,500 times the size of our solar system. This is a big cloud. And in these clouds, every molecule and dust particle and atom is attracted to every other one. And if I go back and explain this, the ones on the outside get pulled to the inner part. And so this thing is going to collapse. And as it does, there are some areas that are denser than others. They collapse a little faster. And you'll see this in this simulation. And so the column density is just how much stuff are you looking through in this. And so I'll run this little animation. And so that's how it looks. And we'll stop. So where it's getting brighter, that's where it's getting denser, and so stars are going to be able to form. And you'll see now it's just changing the scale because it's getting so dense it had to change the scale. And so we'll zoom in, we'll turn around and then zoom in on this densest part and again change the scale. And then these bright things that come flinging off, these are still larger than the solar system. So the span of the whole thing is 5,000 times the solar system. So each of those is still 1,000 times the size of the solar system. And you can see it spins off disks and little things that will become stars and their attendant planets. And this whole process takes tens of millions of years, if not hundreds of millions of years. And we see this going on in the Orion Nebula now. When you look, if you Google it and look at the Hubble Space Telescope images, we see forming solar systems. So we're pretty confident in our model because we've made predictions and then observed in the sky the kind of stuff we've predicted. So that's the basic process. And so all of those white dots are forming solar systems. So they form from clouds of gas and dust. Gravity pulls them together and the knots compress to form stars. Then stars shine by nuclear fusion, where 4 hydrogen atoms get squashed together to become 1 helium atom. And by Einstein's famous E = mc squared, the energy equals the mass times the speed of light squared, they emit utterly huge amounts of energy. because the speed of light is big. It's 186,000 miles per second. You square that and it's a big number. And so the huge amounts of energy, if you fuse 1 kilogram, if you have a liter bottle of water, pick it up, that's a kilogram. And if that were a kilogram of hydrogen, then if you fused that to helium, 0.7%, that's 7 grams of it would become energy. And that energy would yield 175 million kilowatt hours of energy.
Wow.
In Tupper Lake right now, you're paying for 1 kilowatt hour, you're paying 5.49 cents. So if we could fuse 1 kilogram of hydrogen into helium, we'd make $9.6 million. So yeah, it's a very efficient way to produce energy. So this is just a little animation of the process. So we take 4 hydrogen, the protons, and then they come together and they throw out this piece of antimatter, a positron, and then each combined, that's a positron or a proton and a neutron, it combines with another proton, and it releases a gamma ray, and then you've got 2 protons and 1 neutron bound, and that's a helium-3, and then 2 of those come together, and it's most stable when you have 2 protons and 2 neutrons, and then it throws away a couple of protons, and they're free to go back and start this again. And this is happening in the sun right now, even though it's now, you know, off on my western horizon. I know there are some viewers in the west. You could probably still see the sun, so you can see where this is going on. And so then in the lives of stars, they live in hydrostatic equilibrium. So gravity pulls inward as the weight of the upper layers tries to squash it. Remember, gravity formed this thing out of a big cloud. So gravity, it's not very strong, but it's relentless, as all of us who are starting to crumple underneath its continual pull can say. So, and then, so I can illustrate this. So here's gravity. It's pushing in, pulling in, trying to destroy this star. And then there's the pressure of that heated gas, which is getting all this energy dumped into it from fusion, and it's trying to push out. And so the pressure is pushing out, gravity is pulling in, and the star lives this way for, in the case of the sun, 10 billion years. It's a dynamic equilibrium. If it expands a little bit, then the fusion winds down, and so then gravity can pull it back in. If gravity pulls it too hard, then the fusion ramps up and pushes it back out. But ultimately, gravity will win. It always wins. So the sun is a living star. All right. 7 grams of each fused kilogram become energy. And so there's this tiny little number of joules. All right. A joule, if you take your 1 liter bottle of water that has a mass of a kilogram, if you lift it 1 meter, you've done 10 joules of work. So this, you know, this 10 to the minus 12 joules is less than it takes you to lift an eyebrow. The sun shines 3.828 times 10 to the 26 joules per second. So you get 10 to the minus 12 joules out of a fusion. It's emitting 10 to the 26 joules every second. So it's got to do a lot of fusions. It's got to do 10 to the 37 fusions every second. So multiply that by 4, and that's the number of hydrogen protons that manage to fuse in the core of the sun. And so the mass of the 4 hydrogens is this 10 to the minus 29 kilograms, itty bitty. But it turns out that you're using so many of them, that the sun fuses 5.9 kilograms of hydrogen per second. Oops, I'm missing something there. 10 to the 37, 10 to the minus 29. I'm missing some scientific notation. I apologize. That's an error. It should be, there should be a 10 to the 6th there. So that's a million in there. Because, yeah, all right, maybe that is correct, and I'm just flustered because my computer crashed. And so anyway, I'll believe my old numbers. But at any rate, the sun manages to fuse 6,000 USS Enterprises of hydrogen every second. So 40, and so since 0.7% of it becomes energy, 45 USS Enterprise class masses of hydrogen fuse in the sun every second. So if you're standing in the sunlight, if you see the sunlight, start counting by 45s, 45, 90, 135, 180, 225, is that it? 270, and on and on. That's how much mass the sun is converting into energy every second. It's utterly magic. But it's going to run out of fuel because it's a finite size. And so how it will live and how it will die is entirely determined by its mass. So this illustration, here's a really high mass star, Spica, or the stars in the belt of Orion, the nice white stars in there. They go through a super big red giant stage, which Betelgeuse, the red star in Orion, is in this red giant stage. And they end as massive supernovae, explosions of giant stars. And so mid-sized star like the sun, they become red giants, but not as big as something like Betelgeuse. And then in their death throes, they throw off their outer layers, and only the core of the star remains as a white dwarf star. And this is what contributes to the supernovae, the exploding stars that we are using to measure the universe. So sun-sized stars, in their normal life, they get energy from nuclear fusion. The fusion core for the sun is about a quarter of the radius. That is, the part of the sun that's hot enough for there to be nuclear fusion is about a quarter of its radius. And the sun will last 10 billion years using its fuel at the rate it's using. So let's look at the sun. There it is, right here on your screen. So here's its diameter is about 865,000 miles. Its fusion core is about a quarter of that. Here's the size of the Earth, about 8,000 miles. So these things are not to scale. So let's scale them. There's the Earth on the scale of the sun. It's 1/100th of the sun. And so the fusion core in the sun, so the sun is 100 Earths wide. The fusion core is 17 Earth diameters wide. So that's how it can fuse 6,000 aircraft carrier masses worth of hydrogen every second. And in its life, it fuses the mass of Earth worth of hydrogen every 316,000 years. So it's fused the mass of the Earth numerous times in its 5 billion year history. All right. So at the end of hydrogen fusion, it runs out of fuel in that. Well, that core is going to cool because it's not producing heat anymore. It cools. So it starts collapsing because gravity is getting the upper hand now, and it will win. And this core gets into a weird state of matter where it's called degenerate. And it doesn't expand when it heats, and it just sits there, and it doesn't absorb as much heat as it used to when it could expand when it heated and stuff like that. It's just heat is getting dumped into it, but on the outside, since it shrinks, more hydrogen gets brought into that heat, fusion core, and so it now gets hot enough that it can start fusing. And that fusion energy, some of it goes into the core, but a lot of it goes out into the outer layers of the star that heat up and expand away from the star. And when you expand a gas, it cools, so the outer layers become red. So well, I'll get to that in a minute. Let me show you this. So here's the sun as a red giant star. All right, yeah, I know it looks the same, but the diameter now is about the orbit of the Earth. So it's a bit bigger. And there is its shrinking helium core. And then here is a shell of hydrogen that is fusing around it. This is not to scale. All right. The fusing shell is still about 25% of the sun at the size it was. But if I showed that on this scale, you couldn't see it. So it's a bit of a lie. So we have the fusing hydrogen shell, the shrinking helium core, and all that heat from that fusing shell is really getting dumped out into the outer layers, and they expand away from the star. That's why it's now as large as the orbit of the Earth. That's why Betelgeuse is so big. Betelgeuse is so large that if we put it where the sun is, the outer layers of it would reach Jupiter. That's how huge Betelgeuse is. All right, so you've got this expanding star and it's getting heated, and eventually the helium core eventually begins fusing. And then you get the buildup of a carbon core, and that'll never fuse. The star just isn't big enough to get it hot enough to fuse carbon into heavier elements like oxygen and neon and things like that. And so the outer layers that are getting heated just keep blowing away, and they blow off as a planetary nebula. And the carbon core remains as a white dwarf star. There's one in the local neighborhood in a constellation called Lyra. And if the clouds weren't here and we could observe tomorrow night, we could point at the Ring Nebula in Lyra. And this is actually an image taken by our own Seth McGowan, in his beginning astrophotography. And it's better than any I've taken. Here's the white dwarf star lurking in here. And these are the expanding outer layers of what used to be a star, probably around the size of the sun. Well, let's look at a Hubble Space Telescope image of this. Yeah. And so now we can see even more of these expanding outer layers. And when we look in infrared and X-rays, there's a lot more going on. This is a very violent kind of, it's a slow motion explosion, but these things are really moving away from the white dwarf fairly quickly. All right, so that's one type, but what we're going to focus on is not the expanding outer layers, but that white dwarf star left behind. So in binary star systems, and most stars are born in binary systems. The sun seems to be a little unusual in being a solitary star. And these two stars, they have different masses. So they evolve on different time scales. And so here's a little table, typical star masses, and these are for different classes of stars. So the sun is, in here, and the sun will live for 10 billion, right here, 90% of the size of the sun. And so the sun will live for about 10 billion years. 1.25, it lives for half of that. If you double the mass, it lives, only for less than one tenth of the time. And look at this, when you get to these really massive stars, they, live fast and die young. A 10 million year old star popping off, But the smaller stars, look at this. 32 billion years for one that's about half the size of the sun. One that's 20%, over 200 billion years. the universe isn't old enough for these to have evolved. So here's this thing I had on the earlier slide that I skipped, that no star smaller than 80% of the mass of the sun has lived out its full life yet. They're all still living. And when they die, when the more massive stars die, no matter how they die, most of them do not destroy their companion star. The other star keeps living its life. And so what that means is a white dwarf can have a companion that is a red giant or even a midlife star. So here's an image of what that might look like, because now the red dwarf star can get much closer to the companion than it could when it was a big star, and stars always slowly spiral in toward each other as they lose energy. And so here's the companion star that's in its gigantic red giant stage. And so the white dwarf is actually able to pull material off of its companion, and it spirals in and eventually falls onto the white dwarf. But a white dwarf can't grow bigger and bigger and bigger because it's this weird state of matter. So here's the material being pulled on, and then there's that red giant companion. All right, so the white dwarf takes mass from the companion, but at 1.4 solar masses, then there's enough pressure and enough heat in the interior that it begins nuclear fusion. And when nuclear fusion begins in the white dwarf, it's like the whole thing fuses at once. It's a spectacular thermonuclear explosion. And so it explodes as a type 1A supernova. And so this shows the white dwarf absorbing. This isn't to scale, this should be much bigger, but for illustration purposes. So the stuff is falling on the white dwarf. This is the supernova thermonuclear explosion, and this is the supernova remnant that has some, this one indicates it has a neutron star in the middle. It can have, or a black hole could be in the middle. So we see these events as they happen, and it was one of these events was observed in 1054 by the Chinese and by the Anasazi Indians in New Mexico, who marked it with a petroglyph. And this gave rise to a nebula that's also in the sky this evening called the Crab. No, it's not in the sky this evening. It's in Taurus, which is in the winter skies. And so it's called the Crab Nebula. And we're still seeing this explosion happen. The stuff is still moving out in this explosion because explosions never stop in space. They just keep going forever until, they're just so diffuse you can't tell that was an explosion. But think about what ends an explosion on Earth. You have an explosion, everything falls to the ground. Well, that doesn't happen in space. They just keep going. So we've been watching. We're coming up in 2054. It'll be 1,000 years since we saw this star explode, and we're still watching it explode. It's just amazing. All right. So when these explosions happen, they shine brighter than entire galaxies. They dump so much energy. It's like they dump in a few seconds, or in a few days, the energy that the sun will produce in its entire 10 billion year life. That's how powerful these are. Incredible. And they're very handy for us radio astronomers. I don't look at these things. I don't look for them. Other people look for them and find them and measure them, but I use them my group uses them for very important measurements. So type 1A supernovae. In this explosion, remember, stars are powered by fusion of hydrogen to helium, helium to carbon, carbon to oxygen, and nitrogen, and on up. And so in this explosion, these very heavy elements are made. And so this, I love this diagram. So the green is from the Big Bang. So hydrogen, helium, lithium, and that's about it. And then dying low mass stars are the yellow. And so there's some heavy elements. So this is in the planetary nebula that we get yttrium and barium. Any of you had been able to drink some barium? Yeah, it's the product of the death of a low mass star. That'll make it taste so much better. And and then exploding massive stars is the orange. These were the ones that died just their life. They end up, these massive stars, they end as a type 2 supernova or a type 1b or 1c, but they end as a type 2. And notice that for us, we're mostly orange here, 73%. We're mostly made of the explosion products of gigantic stars like Betelgeuse and the stars in Orion's belt. But, so let's look at the exploding white dwarfs. And it's dwarfs in astronomy, not dwarfs. The blue, these are origins in type 1a supernovae. Look at these, all right? Isn't that potassium? Yeah. Calcium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These familiar silicon, sulfur, chlorine, argon, these familiar elements had to be made in the explosion of a white dwarf. Wow, next time you look at a rusting piece of iron, an old screwdriver on the floor of your garage, it took an exploding star to make that iron. And you left it on the floor of the garage. Jeez. And then just for review, the exploding massive stars, yeah, we're made mostly of the stuff from exploding massive stars. Notice we're 1% supernova products, or type 1a supernova products. That's very cool. All right. So, and some of that is the iron in your blood that is carrying oxygen from your lungs. Your lungs, the carbon was made by exploding massive stars and dying low mass stars. So yeah, so you are breathing, your lungs are made of the stretchy stuff because those stars died. All right, yeah, we have to eat animals have to die, plants have to die for us to live, stars had to die for us to live. There are original parents. All right, so these type 1a supernovae, the light curves. This is, so down here, I have how bright it is over the days. And so they ignore these numbers, I'll explain them in a minute. And so they get brighter and then they peak and then they get dimmer. Well, they peak primarily because the supernova creates these unstable elements of 56 nickel and 56 nickel that decays to 56 cobalt. And then 56 cobalt decays to 56 iron, which is then more stable. And so they're not quite alike, but we can take into account those variations with spectral fitting. And so we can take this collection of light curves and we can manage to fit them. And notice now they all come to about the same brightness. That is really important to astronomers. And so we can adjust these to get all the peak magnitudes to be the same. So we know how bright they are, how much energy is coming out of them, how bright they should all be. All right, so that brings us to the inverse square law, because distance is really hard to measure in astronomy. That's the big bugaboo. Oh, if we could just figure out measuring distances, and we bootstrap our way. And it'd be really handy if all the stars were the same brightness and all the galaxies were the same brightness, like a 100-watt light bulb. And then by saying how bright it appears, we could say how far the 100-watt light bulb is. And because how bright it appears varies with the square of the distance. So here's light spread. And so here's at 1 meter, all right, it covers this square. At 2 meters, it covers 4 squares. All right, at 3 meters, it covers 9 squares. And out here, it covers 16 squares. It goes down as the square of the distance. And so we can measure the apparent brightness with our telescopes because we look at it and measure how much energy we're getting from it. And then if we know the actual brightness, we can figure out the distance. Because getting the distance, I mean, in the solar system, we can get the distance. We can use radar, but we can't use radar on galaxies. You know, they're really fuzzy things and they're really far away. We've sent radar signals to them. It'll take a few 100 million years for that signal to get there, and then a few 100 million years to get back. I don't think we'll see it. So now, Henrietta Levitt, one of the forgotten astronomer, here's a link down here. And Henrietta Swan Levitt, who lived from 1868 to 1921, she was one of the astronomers at the Harvard College Observatory. These women who did fantastic work and are now finally getting the recognition that they deserve. And she coined this term. We need standard candles. Yeah, we need 100-watt light bulbs. We need objects where we know how bright they are intrinsically. Well, we've got type 1a supernovae. So these are standard candles. So these magnitudes, this plot I showed was calibrated in magnitudes. And these are the brightnesses of the stars. Now, Hipparchus, one of the Greeks in 200 something BCE, he said, well, let's have a sensible system here. 1 is brightest, the 1s are the brightest, the 2s are the next brightest, blah, 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 up to 6. Humans can see about magnitude 6. Well, that means, this is eye rolling. Small magnitudes are bright and large magnitudes are dim. So Hipparchus's system makes sense until you start using it. So apparent magnitudes. So how bright does the sun appear on the magnitude scale? Minus 26.74. There are no units, it's a magnitude. The Andromeda Galaxy, its apparent magnitude is 3.44. M is the absolute magnitude. It's actually the magnitude the object would have at a distance of 32.6 light years. And so the sun at 32.6 light years would be at almost 5 magnitudes. So it'd be a pretty dim star. The Andromeda Galaxy at 10 parsecs, which actually we'd be inside the galaxy, but it'd be at minus 21.5, not as bright as the sun, but only because it's more diffuse. And it's 32.6 light years away as opposed to the sun that is 8 light minutes away. Now these two are related by distance. Here's the absolute magnitude is the apparent magnitude plus 5 minus 5 times the log of the distance. Why is there a logarithm? Because of these things? It turns out our eyeballs, we say something is twice as bright. No, it's not. It's actually exponentially brighter. And so we've calibrated this now with energy, you know, putting a 100-watt light bulb at different distances. And so this is now what we can use. So again, it's this simple equation. If we know how bright it actually is, and then we can measure how bright we see it to be, we can calculate the distance. That's really handy. And so the difference in these magnitudes is mu. Mu is equal to the apparent magnitude minus the absolute magnitude, and it's 5 times the log of the distance over, actually this is 10 parsecs, which is a silly unit, but it just notice that when you take the log of something, that thing can't have units. So we have to divide out the units. So ignore that. It's just 5 times the log of the distance. And so we can calculate the distance. The distance is 10 to the mu over 5 plus 1. Cool. All of a sudden we can measure the distance. The supernova people, they measure mu because all the supernovae have similar peak magnitudes. And so then we can calculate, the spectra allow us to calculate the absolute magnitude, and voila, we know. Now, this little m, it varies due to the Milky Way has an interstellar medium. There's gas between the star. The host galaxy is different. The supernovae vary in their composition a little bit. And so there is some variation in this. All right, so the big conclusion, the takeaway is, wow, if we watch a supernova over time and we plot how it evolves and do a little fiddling with the data, we can say how bright it is, we can measure how bright it appears, and we can calculate the distance. Woohoo! We can find the distances to galaxies, distant galaxies. So the work I do is is looking at galaxies in radio. And so what we're trying to do is put together our observations of galaxies with models of the universe. And so there's this thing called the cosmic background radiation, the explanation of which would take me an entire other talk. And so basically this cosmic background radiation gives us the temperature of the universe before there were stars. And so this is our image of it. This is the full sky, and the signature of our galaxy has been removed. And this was the Planck satellite. And here's the URL if anybody's interested. And on this, the reddest red is 1/1,000,000th of a Kelvin. A Kelvin has the width of a Celsius degree. So 1/1,000,000th of a degree Celsius hotter than the bluest blue. Tiny, 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 tiny fluctuations. But where it's a little warmer, that indicates that there's a little gravitational collapse going on because there are collisions. And most of us are of an age where when we were children, a part of our anatomy got warmed by collisions if we did not behave. So we do know that collisions result in warmth. Just clap for a bit. All right. And so even some of my students understand that. I thought they all had enlightened parents, but all right. So what we are seeing in the orange parts are dark matter attracting some normal matter and heating it up. And dark matter is this stuff, we don't know what it is. Galaxies, from the matter we see, we add up the masses of all the stars and all the gas we can see, and there's not enough matter there to hold the galaxy together given how fast it's spinning. They should all fly apart, but they don't. And so why? Well, there must be something providing gravity that we can't see. Well, when you have a problem, name it. All right, let's name it dark matter. What is it? We don't know. We're working on figuring it out, but we're operating on the model that it's there. All right, so this dark matter, whatever it it doesn't glow, but it has gravity. And so where the stuff is starting to collapse in these hotspots, this is where galaxies will form. And so what we need to do is use computers. There's gravity is there. Let's add time and see how the universe evolves. And so this is a current cottage industry. The Millennium Simulation was one of the first of these, and it says, take the cosmic microwave background or the cosmic background radiation. I apologize, I use the different terms interchangeably. Add gravity and time. Well, gravity is already there, but let's put in the distribution, put in gravity, and then run it forward in time, because we know Newton told us how gravity works. He was a smart guy. and then let's let it evolve. And so on this simulation I'm going to show you, 50 megaparsecs per H. Okay, yeah, we're geeks. We like weird units. Is 230 million light years. And Z is a measure of the time before now. So Z equals 20. This is basically the beginning of time. So let me show you the simulation. And so here it is, Z equals 20, that's T equals 0. Here's the 50 megaparsecs. So this line is 233 million light years. So the bright spots, those correspond to the red spots, and then these correspond to the blue spots. And so this actually, it's not T equals 0, it's T equals cosmic background radiation, which is actually about 300,000 years after the Big Bang. But this is what we see. So let's let time evolve and see where it's a little lighter blue. That's where there's a little concentration of matter. And remember, the bluest blue has a concentration 1/1 millionth greater than the darkest blue, the brightest blue compared to the darkest blue. All right, so let's let time go forward. And now is T equals 0 or Z equals 0. So at about 10, where the universe is about 6 or 7 billion years old. So here we go. So the stuff is falling in toward the brighter colors. And so the oranges are showing up where the stuff, there's no dark matter. You're not going to get any galaxies forming in there. You're going to get the galaxies forming in here. This is going to be a galaxy cluster. This is a galaxy cluster. This is a galaxy cluster. This is a void. These, and so what my group is looking at, so we're living here in one of these clusters. It's called Laniakea. And, I'd have to give a whole series of lectures to get this, get all of this straight. But at any rate, we live in a big supercluster of galaxies called Laniakea. And we live out in the hinterlands. And we look across a void at what we think is a dark matter filament, along with which a bunch of galaxies are strung. And we've named this, because we named it from seeing the images of these galaxies, we named it the Pisces Perseus supercluster. And it's a wall of galaxies, all at about the same distance from us, as though we're sitting here and looking at this thing. And what we want to do is find the mass of that thing. We can observe the galaxies. We observe them in radio, but they don't tell it. We don't know their distances. So, radio observations of galaxies. We don't get the pretty pictures. And this isn't much of a pretty picture anyway, because we look at little faint, little fuzzy things, little dwarfy galaxies. When we look in radio, we see this. So this is basically the brightness of the galaxy. And this is frequency, although we've changed the units to velocity here. So what this gives is that what Edwin Hubble found was that the universe is expanding. That's the whole theory of the Big Bang. All galaxies are moving away and the more distant ones are moving away faster. And so the universe is expanding is the easiest way to explain that. And so when you look out at the galaxies, they're moving away. The more distant ones are moving away faster. And so this galaxy is moving away from us at about 62, 63, 63, 64. So it's moving away from us about 6,300 kilometers per second. Yeah. Okay. It's zippy. It's really moving. But look at this. This side isn't moving as fast as that side. Does that make sense? Was it stretching? No, it's rotating. And so one side is coming at us, so it doesn't look like it's moving away as fast, and the other side is going away from us, so it looks like it's moving away faster. So the middle of the galaxy is moving at this, This side is the side that is rotating away from us. And so it's looks like it's going away faster. This one looks like it's going away slower. So this difference tells us how fast this thing is spinning. So we know how fast it's spinning. And then since all of this is the light from the galaxy, the radio light, we can add it all together and we can say what mass of gas it took to create that much radio light for us to observe with our telescope. It's like, you know, how many photons did we catch in the few minutes we were observing it? So the radio observations give the speed of galaxies, and that speed, what does it do to? I said the universe is expanding. Yes. And so part of the speed is due to the expansion of the universe, but not all of it. Remember, we're looking out at galaxies that are falling into a filament of dark matter. And so if we know the distance, the expansion speed goes as the distance. We know this, times a constant called the Hubble constant. And now and then you'll see in the New York Times science section that the Hubble constant has been changed again. Yes, astronomers don't agree on what it is. We're working on it. It's a hard number to figure out, but we have a ballpark. So that is the speed of expansion. If we know the distance of the galaxy, which we get from the supernova, then, well, we know how fast its expansion speed is, and then we look at what speed does it have. And it's not the expansion speed, because there's this peculiar velocity, which is our name for the velocity at which it's falling into the dark matter. It's our observed, the speed we observe it having from the redshift minus the expansion speed. And so when we find that peculiar velocity, this is what we're looking for in these galaxies. We find that, what we find is the mass that the galaxy is falling toward. So even though we don't know what the dark matter is, we can measure its mass. And if we have this whole string of galaxies along this filament, we can measure the mass along the filament and learn even more about this structure of the universe that is utterly amazing to me. I mean, it looks so much like a neural network, you know, and so that's what we're doing with the supernovae, is using these as our standard candles so we can figure out how fast our galaxies are falling into dark matter. And it's very exciting stuff. So all I can say, as I say all the time, oh, not that one. I meant to take that slide out. The adventure continues. Da-da-da-da!
Wow. Well, Eileen, I hate to say it, but that all makes perfect sense.
Cool. I hope so. You know, stars are pretty simple. You make one with hydrogen, gravity, and time, and you kill one with hydrogen, gravity, and time.
Yeah.
And just to think that all of that stuff, you know, on Earth managed to make bunnies and butterflies.
Wow.
People, astronomers.
It seems so much more organized when it's explained this way.
Well, you know, they pay me to do this stuff.
That's true. That's right.
So let me stop my share.
We did have a couple of questions pop up in the chat.
Cool. I took that down.
I would encourage anybody who had a question just to unmute and let's
that's
enjoy each other's
easiest.
company.
Let's chat about it.
Yeah. I think Tom had a question. Tom Find. Are you still with us, Tom? I'm not sure Tom's still with us.
Okay. All right.
Can I just ask how long the supernovae, how long are they bright so that we can see and study their brightness?
If I bring back my slides, let me find the slide here and show you that plot. So let me go back to share screen. And here, yeah, a month.
Wow.
And so when we see these things, so the supernova hunters, the people that are looking for these, what they do is they observe the sky, big swaths of the sky every night. And then they compare the images to each other and look for, oh, look, there's a new bright spot there. And so they hope they do this frequently. And the work I'm doing, my group, since our telescope fell down last December, the Arecibo radio telescope, the platform fell in the dish, we got to find a new gig here. Yeah. And so we can use the Green Bank radio telescope, and we submitted an observing proposal for that after the end of this summer. And there's a new telescope coming online called the Rubin Observatory, and it's in South America, in Chile, and they are going to look there. It's a 10-year project. We think they're going to start it. They're trying to start in October of 2023. They're still building the instrument, and they are going to look at the entire sky that this telescope can see. So it's going to be completely automated, and it's going to, it's going to be very systematic. And so they're arguing about cadence, all right, because you got to balance between looking for a long time at a patch of sky and looking at all the patches more frequently. Mm-hmm. So right now there's blood being shed. Duration versus frequency. But I'm not in that fight, thank God. But that observatory, it's all going to be automated. The data stream, the software, the analysis is all going to be automated. They're going to produce 20 terabytes of data per night for 10 years.
Wow.
Astronomy, young astronomers will be busy with this data for their entire careers. And so they're going to find a lot of supernovae because they keep looking at the same patches of sky. Mm-hmm. And so what we figured we can do is get the information on those supernovae and then observe the galaxies in the region we want. We know the distances, we can find the peculiar velocities, and we can work on finding the mass of this filament of dark matter. So, yeah, so, they're only up a few days, so you really have to be going back many times, very frequently.
Yeah, or for a long period of time.
Yeah, but if you watch one galaxy, a supernova goes off in a galaxy like once a century.
Oh, okay.
So you got to look at more than one.
The Crab Nebula was one of the first that we
that was
the
1054. Yeah.
Right. Okay.
Yeah. So I did see a question just popped up. How do we tell the difference between type 1 and type 2 supernovae? It's all in the actually in the spectrum, and that's why they have the different names. If you Google supernova and you go to the Wikipedia page, they'll show you that the type 1s and type 2s had different elements showing up, cobalt and iron and hydrogen and stuff like that. And so that's how we can tell those apart, is from their spectra and the composition primarily. So, because the type 2s are the massive stars that have already, the massive stars fuse a lot of heavy elements up and including iron. They don't fuse anything heavier than iron, because when they create iron, the iron core is actually what kills them, because they can't fuse it, and then they explode for a lot of the same reasons the white dwarf stars do, but it's slightly different. So they have a lot different mix of elements in their spectrum than the supernovae from white dwarfs do. So, and
that filament that we're looking at across the way there, across the neighborhood, how far away is that then?
oh geez, yeah, I had to. I'd have to do a calculation.
We don't have to do that now. Just
it's about 5,000 kilometers per second. so yeah, I can do a quick calculation, but yeah, it's probably, I mean, 100 million light years is a good, probably a good number.
Okay.
200 million light years, that a few 100 million light years, which is really the very nearby universe.
Mm-hmm.
All right, the universe stretches out billions and billions of light years away, because for 13.8 billion years, it's been expanding at nearly the speed of light. So it's much bigger than 13 billion light years. And so, yeah, this is still the local neighborhood. You know, and remember that cube, the Millennium Simulation, was only over, you know, about 500 million light years, 800 million light years. So it's still the local neighborhood.
Yeah.
Yeah, we can go over there. You know, there's a nice little bar.
What other discussion or questions do we have? Anything else out there?
Let's see. Oh yeah, Tom asked about TC and technetium, and yes, I don't know. I couldn't answer his question, so that's good. Okay. Let's see. Does the amount of cosmic dust vary enough to significantly affect the expansion rate? No, the expansion rate, I mean, what we were expecting all through the 20th century was that the expansion started at the Big Bang and it was supposed to be slowing down. And then right at the end of the 20th century, the Supernova Hunters discovered that, no, it's speeding up. And we have no idea why. But again, we've named it. It's the dark energy. But now the stars and galaxies barely affect the expansion. But what the dust does is it dims everything. And so when we look at these supernovae, they're dimmed by the fact that their light passes through their own galaxy and then through our galaxy before it gets to us. So.
Right. Great question.
Yeah, other questions?
Well, if not, I can't tell you how much I appreciate your talk tonight.
Well, thank you to everybody for coming out. You know, I talk to myself all the time, so it's really nice to have an audience. Thank you. Thank you.
Big
yes,
round
and you know, my sister and my cousin and a dear old friend are on this, and some dear current friends, and so yeah, it's very exciting. So thank you, everyone.
It takes something so large and puts it in perspective for us, I guess.
Well, and it's where I live, you know.
Yeah.
So, and I love sharing it without having to give a quiz.
Great. I was
or
afraid
wear a mask.
I was afraid there was going to be a quiz.
No.
So within the next day or two, we'll post this on our YouTube channel, and you can
send that out to everybody who registers.
You know, that's a good question. I'm not sure if we do or not. I think we can.
Okay.
I know we send it. I think we send it to our member list.
Yeah.
So if you're not a member, that's a great another great reason to become a member of the Adirondack Sky Center and Observatory. And I can again post the information for contacting us in the chat area.
Yeah, on the website, there must be a link to the YouTube channel, is there?
Yes, I'm pretty sure there is.
Okay.
Probably under the events section, I think.
Okay.
But
Great.
yeah. So Jeff says, yes, there is. So
Yay.
if anybody knows, it would be Jeff.
Okay.
All
Yeah,
right,
there's
everybody.
in the chat is the YouTube channel and Facebook and donate
Right. Yeah.
so we can keep this going.
All right, everybody.
All right. Thank you, everyone.
Thank you and good
Bye,
night.
Kate.
We'll see you
Bye,
next
Cindy.
month.
Bye, Tom. Bye, Mark. Bye, Jeff. Okay. Good night.
Good night, Eileen. Thanks again.
Thank
Great
you.
show. Absolutely great.